Okay, welcome to Math 230. We're going to ignore that section right there because it really doesn't matter what section that says, although it was typed up for a different section at one point. This is going to go for all the Math 230 online courses. So the goal of these videos is to give you somewhat of a lecture without actually being in an actual lecture class. I know some of you are going to learn better this way as opposed to just literally reading a book. So these are kind of like lectures as if you were in class. The only difference is you're not going to be able to stop me and ask me a question right away. So you're going to have to write that stuff down, take notes on your own copy there. All right, so let's go ahead and jump right into this thing. You should have already completed some kind of uh, a pre, um, like not a pre-algebra, but like a pre-calculus type of review, which does have algebra in it. So I'm going to assume that a lot of the algebra that I'm doing here is not something which is foreign to you as we go through this. Few things to know to be successful in this course is you do need to have pretty strong algebra skills. If this was a regular calculus course, I would also say that you needed to have strong trig skills, but there really is no trig in this, so you can relax from this. So Math 230 is really more of a business calculus. Now it is calculus, so we're going to be taking a lot of higher level math and we're going to put it into this. The very first concept is a concept called a limit. And that's what we're going to talk about here in section 1.1. We're going to talk about limits numerically and graphically, as you can see here. Our objective here is to find the limit of a function if it exists using a numerical and a graphical approach. Vocabulary is going to be essential when it comes to this course. I will use a lot of vocabulary, some of which is not necessarily listed here, but right here you can see that we have limit, left limit, right limit. Really, that's abbreviated. It should be left-sided or right-sided limits, but we'll call them left and right. It's fine. So what we want to do is we want to go ahead and take a look at this graph to give you the idea of what this is. If we look at the graph at the right, the filled in dot right here is the point 1, 0. It tells us that f of 1, or the function, which is this big graph, evaluated when x is 1, because this right here is your x value, the 1. It tells us that the y value, that's what f of something is. It means you're going to try and find the y value of the function. The y value of the function, well, the y value right there at that dot is 0. So it simply means when x is 0, I'm sorry, when x is 1, y is 0. That's what f of 1 equals 0 means. However, answering that question, what we've done is we've lost some information, as it says here, about what happens to f of x as x values get close to 1. And now we're going to start approaching the idea of a limit. If we look at our graph goes in this direction as we get closer and closer to x equals 1. And then the graph goes in this direction as we get closer and closer to x equals 1 from the other side. What you can see here is x is getting closer and closer to 1. As the x value here is getting closer and closer and closer to 1, the y value appears to be getting closer and closer to a value of 2. But what you can see here is right there, there's a hole in the graph. It's an exaggerated open circle in the graph. That doesn't really make any difference when it comes to the limit. Okay, so what we're saying is, how would you describe what is happening as x gets closer and closer to 1? Well, the graph appears to be approaching the y value of 2. We know that the graph is not the y value of 2. We know that the graph has a y value of 0. It's right there. But it appears that the graph itself is approaching a y value of 2. Okay, this is the general idea behind a limit. So in calculus, we're going to describe this behavior using the word limit. And what we would write for that is the following notation. This notation right here, which will become very, very common in what we're doing. And how we read that is the limit as x approaches 1 of f of x equals 2. So what that's saying is, what does the y value of the graph approach? It's not necessarily the actual y value of the graph. It's what is the y value approaching. The y value of the graph does not necessarily need to be there, or it does not need to be the same for that limit. So the definition, as x approaches a, that's just any value on the graph. So we're going to write that in here as x, whoops, sorry about that. As x approaches, we use that little arrow, a of f of x, well, then that is going to equal some kind of a limit. We're going to call that limit here L. A limit as x approaches a of f of x equals L. If x gets close to but not equal to a, the value of f of x gets close to L, some finite number, just some value. And it's got to be a unique real number. We're not talking about imaginaries. We're not dealing with any of that stuff here. Okay, and in the note there it says our description here gets close to. It's not a very precise definition. If you have taken calculus, it's done more rigorously through calculus. But for our purposes, gets close to, it's probably the easiest way to define a limit. All right, so let's just do some examples, because this is probably the easiest way for you to figure this out. Find the limit as x approaches 4 of f of x equals 2x plus 3. Justify your answer with a graph, and then use correct limit notation to express your answer. So the easiest thing to do, first of all, is to graph this. Well, this is a linear function, so we're going to go ahead and graph it. It's 2x plus 3, meaning that the y-intercept is 3. Let's go ahead and put some tick marks on here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This is not going to be a perfect graph by any stretch of the imagination. I'm just doing my best here to get a good visual. So the y-intercept is 3, which is about right there. I know that it has a slope of 2. So I'm going to do a rise over run here, up 2 units and then right 1 unit. It's going to give me my second point right about here. Don't forget, then instead of a rise over run of 2 over 1, I could also do a rise over run going down. So I could go down 2 units and then left 1 unit. And if I've done a good enough job there, that looks like that's going to create a nice little line. Okay, and there's a sketch of my graph. And let's see here, as x approaches 4. Now, it's not going to be easy to see here because, and you'll understand why I'm saying this in a second. If I go to x equals 4 on my graph, 1, 2, 3, 4, and then go up to my graph, whoops, it's not the color I meant to have, but that's okay. What I would have to do is I would have to figure out, okay, now as x is approaching 4, what does this y value seem to be approaching? Well, I didn't put enough tick marks on there. But here's the thing, 2x plus 3 is just a line. There's no holes in it, there's no breaks in it, nothing like that. So really, if I just plug 4 in, I'm going to get f of 4, which is 2x plus 3, so 2 times 4 plus 3. So f of 4, that is horrible writing, I apologize, is going to be 8 plus 3 is 11. So f of 4 is 11. So it looks like the y value that we're approaching there is 11. So if I want to write that in proper limit notation, it's going to be the limit as x approaches 4 of the function. Now I can either choose to write the entire 2x plus 3, or I can just write f of x equals 11. And that is proper notation. And we've kind of sketched it with the graph so you can see it, what it is that we're looking there. So I definitely did not draw this correctly to scale, because I should have gone up to 11 tick marks on the graph. But hopefully that makes enough sense. Okay, let's go ahead and take a look at the next page. There are times on graphs where limits fail to exist. The first situation, like the one that we see here on the left, situation 1, what you can see is as x approaches 0, and that's the, whoops, sorry about that. As x approaches 0, right there, if we follow the graph as x approaches 0 from the left-hand side of 0, okay, x is now approaching 0. The y value seems to be approaching 1. As x approaches 0, however, from the right-hand part of the graph, the y value now seems to be approaching -1. So as x approaches 0 from the left, I'm sorry, I think maybe I said it was 1, it's 2. As x approaches from the right, as we approach 0 for x values from the right, it appears to be approaching -1. The left and the right-sided limits do not equal each other at 0. In that case, the limit will fail to exist. This is what is known as differing behavior. Differing behavior. Okay, that's one way a limit can fail to exist. The middle one, situation 2, as you can see, is again x approaches 0. Well, the first one, as you approach from the left, the graph is going to keep on going down. It technically keeps it going down forever. It's actually approaching negative infinity. It's going to go down forever. And then as you approach from the right-hand side, the graph is approaching what looks to be going up forever. It appears to be going towards positive infinity in the y direction. Also differing behavior, but this is what is called an infinite discontinuity. We'll get to that at some point. But basically, this thing has a vertical asymptote right there at 0. Anytime there's a vertical asymptote, the limit is going to fail to exist when these things go into opposite directions as they are. This last one, situation 3, will not come up very often. I seriously doubt we'll actually see it again in this course, but I'm going to mention it because it is one of the ways that a limit can fail to exist. What's happening is this graph, as it gets really, really close to 0, as you can see, those lines get really, really dense and dark, and that's because what's really happening, I'll kind of try and sketch it over here. This thing over from the, because it comes from the right side, is bouncing back and forth. It's going to keep bouncing back and forth infinitely as it gets close to 0, and then from the other side, it's going to do exactly the same thing. It's going to bounce back and forth infinitely like this also as it gets closer and closer to 0. It will never actually hit 0. This is what is actually called oscillating. Oscillating. I think I'm spelling that right. And when this thing oscillates, because it's not going to ever hit a specific value, it's literally just going to keep bouncing up and down. It also will not approach any kind of a finite y value. All right, couple of definitions, because I've been mentioning these left and right things. Now we've got notation here to look at. The first one says the limit as x approaches a, and then it's got that little, what looks to be like an exponent right there, what looks like a plus sign. That means as x approaches a from the right-hand side of a. So it's coming from the right, and you're actually going to move towards the left. And I know that can be a bit confusing. Just know that you're going to be looking on the right-hand side of a and seeing what the value looks like it's approaching. So if we go back to the first one, like I said, if we look at this thing from the right-hand side of a, that was this piece right here. That is the right-hand side of a. Well, the limit seemed to be approaching -1, which is what it says right here. The limit as x approaches from the right-hand side, or from 0, from the positive or the right-hand side, the limit was approaching -1. The next definition is just the opposite. It's exactly the opposite of what it is. X is approaching a from the left-hand side now, because that's what the negative sign means. Negative is a left direction, positive is a right direction. So we'll go back up to our graph, and once again, from the left-hand side now, you can see that was this piece, and that's where the graph was approaching +1. So as x was approaching the left-hand side of 0, right here, I keep saying +1. I mean positive 2. I don't know why I'm looking at that and saying positive 1. I must need my glasses on or something. But there you go. So hopefully that makes sense. You can have one-sided limits, which is what these both are. These are called one-sided limits. One-sided limits can exist, while the limit as x approaches 0, as we could see here, limit as x approaches 0 didn't exist on this one because of differing behavior. Okay, they went to two different values as x approaches 0. Okay, so now let's look at these examples down here. We're going to return to situation 1, so I'm going to scroll back up and down. I apologize for that. Let's look at the limit as x approaches 0 from the left. That was done for us. That was actually what we just did in the definition. As x approached 0 from the left, that was the one that approached 2. I got it right this time. The limit as x approaches 0 from the right-hand side, we said was negative 1. And that was this one right here, that one right there. But now let's look at it from a different perspective. Let's look at C. It says as x approaches negative 2. Well, let's go back up to the graph and see. As x approaches negative 2. Well, let's find out where negative 2 is on the graph. Negative 2 is right here. As x approaches negative 2 from both the left side and from the right side of negative 2, that appears that the y value is approaching 0. So we're going to say that the limit as x approaches negative 2 is 0. And then in the bottom one in part D, it says what's the limit as x approaches positive 2 from the negative side, not to be confused. This is why this is in there. Don't confuse 2 from the negative side and negative 2 as the same thing. They are not. Part D says let's find the limit as x approaches 2, but only from the left side. So when x approaches 2, again, let's find positive 2 on here. Let's do it in this color. Here's positive 2. As x approaches positive 2, we are only looking from the left side, which is this piece right here. So what does that appear to be approaching? Well, if I were to kind of come over here, maybe it's 1, maybe it's a little bit lower. Again, my eyes are not the best there. I think it's probably supposed to be lining up with 1. It's really kind of hard for me to see. So the limit as x approaches 2 from the left side of 2 is positive 1. Hopefully you can see the differences between C and D there, and and also hopefully you can see the difference between how we do a left and a right-sided limit. Okay, for our third example, we're going to look at f of x equals x squared minus 1 over x minus 1. First of all, we want to figure out if f of 1 even exists. And here's the reason for that. If f of 1 exists, it's going to probably be easier for us to find a limit. If f of 1 doesn't exist, then we've got to come up with another way. Hopefully you can look at this and realize f of 1 doesn't exist, but let's go ahead and show it anyway. So what we're going to do is we're going to plug 1 in for x's. So f of 1 is going to be 1 squared minus 1 over 1 minus 1. Well, what you get here is on top you get 0, and on the bottom you get 0. 0 divided by 0 does not exist. Anything divided by 0 does not exist. So really what makes this not exist is that piece right there, the dividing by 0. That makes the function not exist at 1. That means there's something going on. Typically when you get 0 over 0 in this fashion, there's what's called a hole in the graph. That was that little thing that we saw before. So when we go to sketch the graph of this, we're going to sketch it with a hole where x is 1. So there's another method to do this. It's called numerical. What can we do is, if we look at the graph, first of all, let's go ahead and graph this thing. The graph is going to look something like this. There's a hole at 1. And then the graph, I believe, is going to look just like this. If I am not mistaken, that is how it looks. You do have the ability to plug this into your TI-84 and take a look at it, and I would strongly suggest you doing that. The one thing is, once you graph this, your TI-84s are incapable of showing the whole, so you're going to have to be able to figure out where that is. Well, if you go to your table function and you plug in x equals 1, it's probably going to tell you undefined. So we need to figure out what is the actual value. Graphically, you can look at what I just did there, and you're probably going to be able to figure out pretty easily that the graph here is approaching 2. But what we want to do is we want to look at it numerically. So what you would do is you would approach this from both sides. You would approach from the left side, and you would approach from the right side. Now again, graphically, we can see, because this graph is pretty accurate here. But numerically, what would we do? Well, we'd have to plug in values that get closer and closer and closer to 1, but they're getting closer and closer to 1 from both sides of 1. Well, if you start off with a value like 0.9, we know 0.9 is pretty close to 1 on the left side of 1. Okay, that's what this part is right here. So if we were to plug in 0.9, I'm going to have to use my calculator for that. You would get 0.9 squared minus 1 over 0.9 minus 1. So let's see, plugging 0.9 into my calculator, I am getting 1.9. 1.9. And that's pretty close to 2, so we probably are right. Let's try something else now. Let's plug in 0.99, because 0.99 is even closer to 2. I'm sorry, is even closer to 1 than 0.9 was. So if you plug in 0.99 into your calculator, I'm getting 1.99. And then you might be able to guess, if I plug in 0.999, that's even closer to 1 now. I get 1.999. It looks like we're getting really close to 2. The more 9s I add after the decimal place, the closer and closer we're going to get to x equals 1, and it's going to get even closer and closer to 2. Well, then we have to try it from the other side. Let's see what happens if we plug in 1.1. So we'll plug 1.1 into everything, and we are going to get in the calculator, so that's going to be 2.1. But 1.01 is even closer to 1 than 1.1 is. So if we plug that in, we get 2.01. And then if we plug in 1.001, again, getting closer and closer to 1 on the right-hand side, that gives us 2.001. So it looks like, from the numeric examples here, as we approach from the left, we seem to be approaching 2. As we approach from the right, we seem to be approaching 2 numerically. So here is the theorem that is the exact definition of what we're going to use for our limit. This is pretty important. A limit as x approaches a is going to approach an actual limit, and we'll call that limit L, if and only if, that is exactly when two things happen. The limit from the left has to equal the limit from the right, and both of those equal the exact same value, L. So if one of the limits is 1, the other one is -1, not going to work. If the limit from the left and the limit from the right both equal 7, then they work. So that's exactly what's going to happen there. All right, last example. Consider the function f of x equals 1 over x minus 2 plus 3. Find the limit as x approaches infinity of f of x. So what that's saying is, as x approaches infinity, what's happening as x gets really big out off to the right-hand side of the graph? So we're going to do this one numerically first. If I were to plug in 10 into my calculator, we get 3.125. 3.125. Okay, 10 is a big number on the graph that we have here because it doesn't actually even fit on our graph. If we were to plug in 100, which is much bigger than our graph holds, let's see, if I plug in 100, that's going to be 1 divided by 100 minus 2 is 98. So 1 divided by 98, and we have to add 3 to it. We're going to get 3.7 0, 1, 0. Okay, again, you can probably start guessing what the y values look like they're approaching, but we'll try it again because, again, 100 is a big number, but in the grand scheme of things which are infinite, meaning just so insanely big we can't even comprehend, 1,000's better than 100. It's bigger, so let's see what happens if we plug in 1,000. So that'll be 1 divided by, let's see, 1,000 minus 2 is 998, and then we have to add 3 to it. And it would help if I typed it in my calculator correctly. And we get 3.001. So I think you can tell that we are getting really, really, really close to 3. Okay, and I am actually going to say that, okay, 3 looks like the limit. How we actually draw that one, because if you plug this in your calculator, what it's going to look like is something that's going to look like this. And I'm really just sketching this by hand, should look something like this. And then as you start to go and approach infinity, it's going to start to go off like this. And what you can see is my line is starting to approach the y value of 3. This is what is called a horizontal asymptote. And we will actually talk about that much more in other sections. Now, this is also going to look like this on the other side, just to finish off the graph. So what it appears to be doing is it appears to be that the graph is approaching the y value of 3 as x tends to go off towards positive infinity, which is out here, like way off to the right. And numerically, it also appears to be approaching 3. All right, those are our examples for section 1.1. I'm going to try to keep the rest of these videos a little shorter than this one. I apologize. This was the first video. It's a little over 27 minutes, but it is still shorter than it would probably have been in an actual lecture class.